Hello guys, myself Kartik Agarwal from IT Roorkee Engineering Physics branch. Today I am going to discuss a real-world application of signals and system, so-called low-light image enhancement. Uh, Moving further, let's first know the basics how a system works. Basically, an input is provided to a system having some transfer function, and it is expected to give us some desired output. In this project, we will be using a matrix of pixel values. Uh, The each value of matrix is a three-dimensional object representing colors in three different domains like red, blue, and green. As far as the transfer function is concerned, we will can take different transfer function for different filters. These can be gamma correction or some mathematical parameters or equations that we are going to use to modify the colors or the brightness of different images and all. Talking about filters, these can be linear and non-linear based on what we want to do to either reduce noise or to change some contrast and else. Moving further to domains, basically low light image enhancement is concerned with two different domains, the spatial and the frequency domain. In this domain, the spatial one, images or the we should say pixels are represented in grayscale formats, basically the same as the red, blue, and green. And along with the spatial XY coordinate, the spatial meaning is basically the location or space coordinates. And going on, we have filters like low and high pass filters and different things that we can perform here are brightness and adjustment, contrast adjustment, filtering, edge detection. The changes to the images made in this are of two different types, local and global. We will be discussing that in detail later. The next domain is frequency domain. Basically, here we are shifting from time domain or space domain to Fourier domain using a Fourier transform technique. The frequencies concerned with the Fourier transform can be low and high based on what changes we want to make on the images. We are going to use those frequency using filters called low pass, high pass, or Gaussian filters. And that's the basics of frequency domain. Let's now have a quick comparison on different domains, spatial and the frequency one. So basically, spatial domain operates on pixel values and are suitable for localized operations like edge detection, while the frequency domain is for global or large scale operations. Spatial domain is a lot expensive than the frequency domain, and it's better to work in frequency domain rather than the spatial one. The basic comparisons are listed on the screen. You can see. Moving further onto spatial domain analysis, we have already discussed how is image represented in a spatial domain. Let's now go on to operations in this domain. The first type of operation are point operations or pixel-wise operations, where we independently change or operate on each pixel. The basic outcomes that can be achieved from these operations are brightness adjustment, contrast adjustment, and thresholding. Uh, let's go on to the next one. Let's now move on to different set of operations known as the local operation. In this set of operations, we do not independently operate on each pixel value, but rather operate along with the neighboring pixels for each pixel. In these techniques, filtering processes are used to get the desired outcome. The different type of common filters are smoothing or known as the low pass filter, mean filter, Gaussian filter, Laplacian filter, and the Sobel filter. The most often used is the smoothing and the Gaussian filter. The next operations are the global operations. In this set of operation, we do not consider each pixel or the group of pixels, but rather consider the whole image. and work upon it to get the outcome. Histogram equalization technique is used most oftenly. I have described it along with a figure. Here in the first figure, we are seeing that for each pixel value, the number of pixels are different inside the picture. So the outcome coming from that pixel is not so good. Now, what this technique does is it distributes the intensity of pixels for different pixel values and give a sort of stable outcome to get enhanced picture. The technique involved here is histogram creation, then distributing that intensity or the pixel values in full domain properly. Common applications of spatial domain analysis are noise reduction, edge detection, and image smoothing. Based on what filters we are using, we can get the desired outcome. For noise reduction, we are using Gaussian filters. Also for the image smoothing, Laplacian filters are used for edge detection. That's why these two are the most often used filters present in the market. The next set of analysis is frequency domain analysis. In this domain, we shift from time or spatial domain to the frequency domain using a Fourier transform. On transforming the image, we can have range, a whole range of frequencies from low to high. It's recommended to work on either on low or high frequencies, but if required, we can work on both high and low together simultaneously. In this frequency domain, image processing tasks like smoothing, sharpening, and noise reduction can be efficiently achieved by manipulating specific frequency components. The common filters used here are low pass filters, high pass filter, and band pass filter. These filters can also be categorized in ideal filters, Gaussian filters, or Butterworth filters. Talking about the techniques present in this domain are compression, edge detection, sharpening, or smoothing, blurring. For each type of technique, we have to use a specific filter to cut off the signal apparently to get the desired output. Based on the technique we discussed, these are the different applications present in the market. Uh, Most of them we have heard already. It's pattern recognition, image enhancement, image compression, most noise filtering. The most common use is the image compression. We all use this in our daily life. Moving on, let's discuss some models to enhance the low light image. The first one I am picking up is CPG net, and the full form is Channel Prior and Gamma Adjustment Network. Here is a diagram to simply show you how it works. Let's go in a little detail. Let's now go a little deep into discussion about this model. Here I have written two equations, I bright and I dark. These are basically representing the brightest and the dullest point present in the image of any color. Basically, if you see C represent any color in green, red, and blue. This is also called the T property of this model. As the process goes on, first the colors of the image are removed. We first make a gray image using this tree property. Then a gamma function is applied so that the brightness of this gray image is increased. And later on, we can add perfect colors to these images using other properties. After that, a hash property is applied on this in this model. This property basically is basically a fusion technique to impart the color to its position. This A technique identifies the problems or imperfection in the images and imparts the proper colors or brightness to each pixel present in the image using line and MSR techniques. After that, after that, the image is downloaded, or we can say is processed properly. Let's move on to the next model. Next model is So before proceeding, let's discuss about this gamma correction and the Cluesian strategy a little bit more. Basically, gamma correction deals with the global changes in the image. It modifies the overall brightness by adjusting pixel values across the entire image in a non-linear way. This technique is effective by correcting global lighting issues such as inadequate exposure or dark images. Going further about the fusion strategies, local and global changes, we have already discussed in the spatial domain analysis. This is same. Let's move on to next slide. Moving on to the next model, which is low light image enhancement. Its methodology is already shown in the figure. Let's go to it one by one. Basically, first we take an original image and apply multiple steps over this image to get a better processed image. The first one we apply is illumination map. This technique analyzes the image and provides us the areas which are dark and light, means segregation of the areas based on the intensity of pixels. Then we apply the same gamma correction as discussed before, and after that we apply PM3D technique, which basically denoises the image. It is used to reduce the noise present in the image by applying collaborative filtering, preserving image details while smoothing out noise. Even after doing this, we use some other techniques also to reduce the noise so that the processed image is much more refined and processed. This is a simple model to increase the brightness or say the contrast of image. Let's now move on to the next slide. So far, whatever we have discussed was a part of spatial domain analysis, or you can say some examples of spatial models. Now let's discuss a frequency-based domain model. The name of this model is DCT, discrete cosine transform. Let's go a little deep in it. In this model, convolution techniques are used to enhance the image multiple times using different techniques in between, or you can say multiple transfer functions are involved in this technique. We will see it one by one in upcoming slides. So the operation goes like this. First, we take the Fourier transform of existing picture to shift from spatial domain to Fourier domain. Then we compress the picture to just focus on low frequencies components. Basically, low frequency represents the noises and the fine details present in the images. Doing this, we reduce the size and increase the chances of refinement better, better refinement. After this, we quantize the image. Quantization means reducing less important data and removing insignificant details present in the images so that while we are shifting from domain to back to spatial domain, we don't get unwanted details present in the images. This is how this model is getting operated. Thanks for your time. I will take a leave now.